Weight is a combination of your mass and gravity. So how much something weighs is a force that's equal to the mass of that object times the local gravitational acceleration, or W equals mg. This actually gives you a tricky way of cutting weight. Let's say you're trying to get underweight for a wrestling match. Just go up into outer space. You still have just as much mass as ever, but with lower gravity, you weigh less. There you go. Pro weight loss tip. Let's consider a farmer lifting some moderately heavy rocks here on Earth from a field to plant crops. He lifts a stone that weighs 40 pounds, which is about 180 newtons in reasonable SI units. The question is, what force does he apply if the stone accelerates at 1.5 meters per second squared? To analyze this, we'll do what we do with a lot of these problems. We'll start with a free body diagram. Here, we'll draw the stone, and we have the mass. But we don't start off knowing the mass. Luckily, because we have its weight, and we know what the gravity is, because it's here on Earth, we can rearrange this and solve for mass in terms of weight and say mass is equal to weight over gravity. I can now plug in that weight and gravity and say here that means as long as it weighs 180 newtons here, it must have 18 kilograms worth of mass. And that's why you can get mass balances that you place objects on and it tells you the mass. And really what it's doing is it's measuring the weight, it's measuring the force that that thing's exerting on the balance, but it's just doing that calculation to give you a mass in terms of grams or kilograms or whatever. So if you were to take those up into space or low orbit, up where gravity is less, you would get inaccurate mass measurements, even though the force measurement, like the weight, would still be accurate, but the mass is not. Anyway, we have the mass of our stone. Now let's include the forces acting on it. We have y coordinate, we'll define our coordinate system, and then we'll have weight acting downward, 180 newtons, and then the unknown force acting upward. So we have our free body diagram. We can now write Newton's second law as a vector. It looks like this, F equals ma. We'll apply that in our coordinate system and say that upwards is positive, and now we'll include those forces. So this will be F is positive and W is negative. So this will be F minus W equals ma. We can now solve for the thing we want to know, the force that the farmer exerts, in terms of the other things by adding the weight to both sides. And so the force that the farmer is exerting has to be at least equal to the weight plus the mass times whatever acceleration it's experiencing. We know that acceleration from the problem statement, so we can plug that in, and we get a force of 207 newtons. Since this is a vector quantity, if I'm trying to report a force, I need to make sure to include a magnitude and a direction. So the force that the farmer is exerting has to be 207 newtons upward.